Woo!
So no pressure at all. I think it's mostly for like post views.
Where do you post the video after? I never went and checked them.
It's on YouTube, but the same link that I sent you will work
Okay, okay.
afterwards.
But is that a channel? So can I see also the previous videos?
Yeah, it is a channel.
Oh, so I'm on YouTube a lot.
Exactly. Yeah. Okay, so it's 10 a.m. and hello everyone. This is
Hello.
our code hour session. So that means that we did not really prepare for it thoroughly. We just have a topic and we're gonna explore it and talk about it live today. So the topic is statistics in data science interviews. So please welcome Annalisa. She is our almost I don't know,
Almost
almost
a
eternal guest. Yeah,
almost a
yeah,
terrible guess.
yeah. I think we should consider you as a part of the team now. So yeah, if you wanted to be. So Annalisa has a very extensive background in statistics and mathematics. So she has a PhD in this, and that means
I forgot
she's.
everything.
Oh yeah, yeah. Yeah, you probably forgot everything, but I didn't even know it. So I'm in a worse position. So yeah, today we're going to discuss maybe some aspects of what people are interested to ask data scientists during the interviews and how could you answer it. And yeah, and I might be this guinea pig.
You will be?
Uh, yeah, so probably we will go like I will try to answer the questions from Annalisa, and then we're going to discuss it and let's see how it goes. Yeah, I'm already a bit stressed. But,
Don't be.
yeah. I'm not. I'm not. I'm at home. Everything calm. I'm doing meditation. So.
Okay. Yeah, I think statistics, I think a lot of interviews for big companies in data science always have either a statistics kind of interview or a few statistics questions, like usually very basics, but to get an understanding that the person knows something about like probability, uncertainty, expected values, and so on, which are then useful for machine learning and data science. Yeah, so should we
Yeah.
start?
I see you're really pumped. Yes.
Okay.
Please.
Okay,
Yeah.
so a typical example, right?
Oh.
Yeah. So you have a
Yeah.
coin.
Mm-hmm.
Um, you can get either a head or tail,
Yep.
and this coin is completely unbiased. So you have 50% of probability of getting head and
Mm-hmm.
50% of probability of getting tail. And then you flip the coin a certain number of times. So let's say you flip the coin 10 times.
Mm-hmm.
And you count all the times you get head,
Yeah.
right?
Mm-hmm.
So my question now would be, um, what what is the expected value? So how many tails you expect to get,
Mm-hmm.
and if you know what is the variance of this, of
Mm-hmm.
the number of heads.
Yeah. So I mean, since the
And you
coin
can
is
start with what kind of distribution this is, and so on and so forth.
wow. Yeah, it's a yeah. So I mean, since the coin is fair, so ideally we should have half heads, half tails. So in our ideal simulation, but of course in real life it won't be like this. And if we flip it like maybe 5 times, it could be all 5 heads or all 5 tails. But the more we are flipping it, the more ideally it should go to our ideal distribution, like 50-50. So hopefully, if we flip it like 1,000 times, we get something like 510 to 490 or so. So our expected value is zero point 0.5 for heads or tails. But yeah, of course, we will have some diversion or divergence from this mean. And yeah, now it goes. So I'm not a statistician. So variance, as I understand, variance here is this like range what we might have, like not
The
0.5.
variability.
Yeah, the probability that so let's say if we have 10 flips, our mean value of heads will be somewhere, for example, 0.4. But we can calculate the variance of it.
So
So
it's the
let's
mean
say
value of head if you have 10 flips, like around 5, right?
no, I mean if you flip the coin five times, yeah, I mean 0.4%, yeah.
Yeah.
Yeah. So like around 0.4% of the times, yeah, but we can calculate what is the variance of it. So it was, yeah, I mean, and if we flip the coin like 1,000 times, maybe our value will go to like 0.48. And we, of course, the more tosses we do, the less our uncertainty goes. So that means probably the thinner our variance becomes, or the less wide. But honestly, I would say that it's not the variance, but it's the confidence interval. And I'm now thinking about the variance, how to bring it up in this use case. Um, 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 so the distribution, yeah, I think it's called. Yeah, I'm afraid to say something stupid.
Go
Bernoulli,
ahead.
that's.
The one flip.
So I think it's called the Bernoulli distribution when we have discrete values, and but one of them is for like counts, and I think it's Bernoulli distribution, right? So when you have something, some discrete values, and they are either happen or not, and then you can calculate your like the mean of it, where you have an expected value.
And if you calculate the sum instead of the mean, like what is the distribution? What is the sum of like flips? Like what is the distribution of the number of heads?
Distribution of the number of heads. You mean if we go with more and more flips?
So basically, so if you flip one coin, right, you get either head or tail.
Mm-hmm.
And this is a Bernoulli. But if you flip 10 coins and count the number of heads,
Ah,
this is
so
the binomial.
is it the Pascal distribution or
It's binomial.
binomial? Okay, yeah,
But yeah.
right, yeah. Yeah, Bernoulli is for one event and binomial for multiple discrete events.
When
Yeah.
you count,
Mhm.
it's basically when you is count. When you
Mhm.
count how many heads. I mean, there are
Yeah.
other distribution for count, but if you count the number of successes,
Mhm.
usually it's, of course, if you have independent events, so independent flips, then
Yeah. Yeah, that makes sense. Yeah. Mhm. Okay. Right, and yeah, I'm trying to go back to variance. Um, so probably variance should depend, yeah, on the mean value, on the expected value, and on the amount of experiments, I guess. Mm, yeah, I'm not sure how to jump in with variance.
um,
So the confidence interval will depend on the
yeah,
amount of intervals, yeah,
yeah.
experiments. Yeah, I
And
mean,
if, like, let's say I flip this coin 1,000 times, right?
mhm.
And I always count the number of heads.
Yeah.
Do you know what kind of distribution this could be approximated with?
Uh, by distribution, we mean that
Probability distribution, yeah.
sorry.
Probability distribution.
Yeah. You mean like distribution? So we toss it 100 times, we get the value. We toss it 101 times, we get the value. We toss it 102 times, we
I
get the value.
say,
Or what distribution?
so I say basically you toss it 1,000 times, you count the number of
Uh-huh.
successes, right? And this is one value. And then you toss it another 1,000 times, and yeah, it goes
Ah,
here. And then you count again the number of successes. Then you toss it another 1,000 times, and you count again the number of successes, and so on.
Okay, yeah. So I guess this is what we call this central limit theorem. Yeah. So
Woo!
yeah. So I guess it doesn't really matter what the initial distribution was, but if we do what you said, so we continuously repeat our experiment, then ideally or not ideally, by this theorem, we should have a normal distribution of this mean value.
And of the sum also.
Yeah, I mean of any statistics, right? Or
Not any, I think, maximum likelihood estimators. I
okay.
think not all statistics, but a lot, like, yeah. I mean, anytime there is a sum or a expected value or some sort of estimator.
Yeah, not mean probably. Yeah. Oh, not median. I mean, because it
Yeah.
will. Yeah. Okay. Yeah. So the mean and the sum, yeah, should follow the normal distribution, and that is kind of useful for practical reasons. So if you don't know something, just repeat the stuff a thousand times.
Central limit theorem. So what's the difference between the sum and the mean? Like, kind of in the central limit theorem.
The sum and the mean.
Yeah.
Well, I mean, the mean is what we usually use because it somehow classifies or yeah tells us what distribution. Because if we have only the sum, we need to know the amount of
So
trials.
we can do a small exercise if you want.
Yeah,
I mean, I've
yeah,
done
of
this
course.
before in an interview.
Hmm.
So, so let's do. So, for example, we have what we have talked about, right? These repeated experiments, and we will have a distribution for the sum and a distribution for the mean, right?
Hmm.
And because we repeat this entire experiment many times, and we want to find the expected value and the variance of this distribution, right?
Hmm.
And let's assume we say n is large enough, and so we can approximate this distribution with a normal distribution, right? But you
Hmm.
want to know what is the mean and what is the variance of this normal distribution.
Hmm.
Okay. So if you have the mean or expected value, right, for the sum,
Hmm.
if the probability of flipping coin was 0.5 or flipping head was 0.5, will be 0.5 times n, right?
You're talking about the sum.
The sum, yes.
Yeah. Hmm. Yes.
And in the other way, and but if you then wanna basically take the mean, which is basically estimate the probability of success, right?
Hmm. Yeah.
The expected value would just be 0.5.
Yeah. Sounds logical.
Yeah, okay. And then we go to the variance, right?
Hmm.
And I will tell you that the variance for one flip, right,
Hmm.
is p times 1 minus p. So in this case, it's 0.5 times 1 minus 0.5, which is 0.25.
Okay. Okay.
It's just
Yeah.
a formula, like for the Bernoulli, the
Hmm.
variance. So for one flip, the variance is p times 1 minus p.
Yeah. So zero point 0.5 squared. Hmm.
And now I'm
Yeah.
going to Google it because I want to make sure I don't say something wrong. Yes. I mean, these are the things I know, but you never know. So it's
I'm pretty
probably,
sure you don't say
yeah.
something wrong.
The probability is, the variance is the probability of success times the probability of failure, right? So 0.5 times 0.5, which is 0.25.
Really, the variance is the probability of success times the probability of
Mhm.
failure. Is it always the case, or it's for Bernoulli?
For Bernoulli. Yeah.
Okay. Mm-hmm.
And so, okay, and so now we have this for one flip, right? And we
Uh-huh.
want to find the variance of the sum and the variance of the mean.
Okay. So, yeah, I mean, the variance of the mean. You mean after we do it 10 times?
So basically, yes. So
Mm-hmm.
basically, we want to find the variance of. So we have the variance of one flip, right? So let's say
Mm-hmm.
we flip it n times, right? And
Mm-hmm.
then we have one distribution for the sum, so for the number of heads, right?
Mm-hmm.
And then we have one distribution for what we call the mean, but which basically would be the probability of success, right?
Mm-hmm.
Because it would be the number of heads divided by the number of trials. So the
Yeah.
estimate of the probability of success, so the sample mean.
Mm-hmm.
So let's call it sample mean. So one is so let's say that x is either 1 or 0. So one is the sum of x, and one is the sum of x over n, which is the number of flips.
Okay.
Tell me if I'm going too theoretical.
No. It's okay. I'm trying to follow you, and it's good. It's good. So the variance in case of many tosses, the variance will be like p to the power of number of ones times 1 minus p to the power of 1 of n minus successes, or
No, so basically when you have the variance, right? So let's say you have two random variables which are
yeah.
independent. So let's not consider the covariance, and then you sum them up. Usually the expected value is the sum of the expected values, right? So like you would expect. And the variance is
The
also,
sum of
yeah.
variances, but maybe
And you
with
don't
some
take into
coefficient.
account the covariance, but whatever, right? So if you have okay, so if you have the fact that the variance of one is p times 1 minus p, the variance of the sum,
Then it should multiply by n.
yeah.
But is it sane?
Sorry?
It's so the variance will be that huge.
For the sum, yes. So for
The sum, right? Yeah.
the sum. Okay, but now is the tricky part, and it's the cool part, because basically is what I mean, at least helps people understand, help my students, sorry, I went in teacher mode, understand that the more information we have, the more we know, the more data we have, the more we know. So we said that for the sum, the variance is n times p times 1 minus p, right? So n times 0.25 in our case. Okay, but now we are like, okay, but we want the sample mean. So what is the variance of the sample mean? And the sample mean is the sum divided by n.
So we're not talking about many trials, so many
Yeah,
times.
always. Yeah. We do 1,000 trials, and every time we take the sum and divide by n.
Okay, yeah, then yeah, I usually use the formula of
So basically,
standard deviation. I think yeah. I mean, we should probably take the sum of residuals and somehow scale it by the number of trials with some. But I'm always confused. Should we divide the sum of residuals? I mean, we square the sum of residuals, sum it, and I think divide by n, or sometimes n times n minus one. This one I don't know when we
so
use.
basically, so you have, okay, so we said that we have the variance of one flip, right? So we have the variance of the binomial, the Bernoulli distribution, which is 0.25. Then we said, okay, let's say we want to, every experiment we take the sum, and we said the sum is n times 0.25, right? And now we say, okay, then now, but now we want the variance of the sample mean. So every experiment, like before, we take the sum, but we divide it by the number of flips in that experiment, right?
Yeah.
So this is the sample mean. So is the sum of the number of successes divided by the number of trials.
Okay.
And so if we do that, we would get something like that. We should get the variance of so we have the variance of the sum, right? And then we wanna have the variance of the sum divided by n.
Yeah.
And this is the variance of the sum. And then every time you have a constant multiplied by a variance, right? Since the variance is, as you said, is a quadratic thing, you need to
Do a square root.
yeah, exactly. So you need to square, right? So we have n times 0.25, and this is the variance, and we have to multiply by 1 over, oh my God, now I'm confused. We need to get a square root, right? We need to get
Yeah. Somewhere.
0.25 over square root of n.
Seems like.
We need to divide it by n, so we have n times 0.25. We need to square the 1 over n, right, because we have the variance.
Uh-huh.
And so we have times 1 over n squared. It should be the opposite, though. The square root should be at the denominator. Why am I doing this wrong now? Am I doing it wrong?
I don't think so. But we're basically counting the variance of one. So we toss the coin 1,000 times, and we're counting the variance for this result, or
We toss the coin 1,000 times, we divide by n, so we have the sample mean, and then we calculate the variance.
okay, yeah, in this case. So, right. Yeah, I mean that sounds reasonable. No, 0.25 divided by
Oh no, I'm
square.
stupid. It is divided by n. Is the standard deviation that is divided by square root of n. So,
Oh, okay.
so the variance of the sum divided by n, which is 1 over n squared times the variance of the sum. The variance of the sum is, we said, is n times 0.25. This simplifies, so we have 0.25 over n. And so the
That's a
n,
variance.
the variance of the sample mean. So n is at the denominator, and that means that the bigger n becomes, the smaller the variance of the
Yeah,
sample mean is.
and that also means that our confidence interval
Exactly.
gets, yeah,
The confidence
smaller.
interval for the mean becomes smaller and smaller the more data we have. We made it.
Yeah.
We should change the topic.
Yeah, but just one step back. So the variance is 0.5 or 0.25 divided by n, but the standard deviation will be a square root of it,
The square root.
or square root of n only.
No, the square root of everything.
Okay, and this stupid question. So sometimes in the formulas I see divided by n, sometimes divided by n minus one.
Yeah.
Is there any
Yeah.
clear explanation on that?
Yes. So basically, so you have your estimators, right? And you want to have some properties for these estimators and for some distributions, and also for estimators not of the mean. So a lot of times, like in our case, right, the estimator is the something the sum divided by n. And then the property we want is that when we take the expected value of the estimator, we get the real mean, so the population mean. So in this case, if the estimator is the sample mean, so it's the sum of the heads divided by n, we want the expected value of this to be exactly 0.5.
Okay.
But in some cases, it's not like that. And in some cases, you will get something times uh, you will get something that is not exactly the case. So to make it unbiased, so to make it that the expected value of the estimator is equal to the real value, sometimes instead of divided by n, you have to divide by n minus 1. And this is usually the second estimator, like usually for the mean, for the first degree estimator, mean or whatever, you need the n. But then when you go to estimate, for example, the variance, then you usually have the n minus 1, and you can, kind of the reason is that you already use some of your, they call it degrees of freedom, to estimate the mean, and you are using this then to estimate the variance, and this is what is making everything unbiased. But I couldn't get now more into details, but this is the intuition, just to make it unbiased. And usually it is for the second degree estimator, so usually for variance, and I don't remember having seen it for expected value or mean.
Okay, yeah, thanks for this. That
You're
makes sense.
welcome.
Cool. Yeah.
Which
So
shouldn't matter if n is large enough in general.
yeah, I mean, if an N is large enough, we don't care
Yeah.
really. Yeah. So cool. Yeah. Let's jump to the some next stuff.
Yeah. Okay. Where do we want to go, Icon? Just
Uh,
let's talk.
I want to go out of the interview, but so,
Okay.
no. It's okay. It's okay to be. So I don't know. We can. If you have something in mind, please just shoot, or we can go to some
I'm
hypothesis
thinking.
testing or.
I'm thinking what I've been asked in interviews before. This thing with the binomial is always the thing, Bernoulli binomial, because it's easy and usually it's the distribution that people know besides
Hmm.
the normal distribution.
Yeah, I also
Um,
know the name of beta, but
the beta, yeah. I've also been asked proofs of this stuff.
proofs of
So,
what?
uh, where can we go?
To
So there is
hypothesis, maybe.
testing, yeah, hypothesis testing. I hate hypothesis testing. Oh my God.
I hate it more. So,
P-values, confidence interval, this kind of stuff.
oh
When do
yeah,
you use the null hypothesis? What is the null hypothesis?
yeah. So I mean, I can just start about it. So
Mhm,
as I understand, when we have some experiment, let's say, we observe some stuff, and then we want to check if some idea is happening or not. So we say that, well, we have this hypothesis and we want to check if it takes place or nothing really is happening, meaning that there is. Okay, no, I should probably pick an example. So I don't know. So let's have yeah, go back to the coins maybe. So we flip this coin a lot of times, and we said that it's kind of a fair coin. So ideally, the more tosses we do, the closer to zero point 0.5 we should get. And we can say that our what's called null hypothesis says that the coin is fair,
mhm.
but sometimes we want to check, well, is it really fair? And we can come up with an alternative hypothesis saying that the coin is not fair. And then it goes to testing of this hypothesis. So we want to run some tests and either so basically, yeah, we want to run some tests and say whether we can accept this alternative hypothesis or we cannot really accept it. Or actually, whether we can reject the null hypothesis or not. So this is very confusing. So basically, there are two hypotheses now: the null hypothesis that the coin is fair, and the alternative hypothesis that the coin is not fair. And then we go for the experiments. So we toss the coin many times, kind of, and so after some moment, so that's up to some calculations, we will be able to say whether we can reject this alternative hypothesis or we don't have, or we cannot reject it, right? Yeah, this one. mm,
Doesn't make any sense, like in general, I think, hypothesis testing, because so basically you want to know if you have enough information in your data or enough data, so both information in the data and enough data to
mhm,
reject the null. So like if you can say the null is not valid, but you
mhm.
actually can never
Say that the alternative is
the
right. Yeah.
opposite. Yeah.
Okay. Yeah. So yeah. So we can either reject null or not reject it.
Yeah.
But that will mean that our alternative can become a null if we reject the null, or not
Uh,
really.
It's hard because all this theory is based on point things. So if you say the coin is fair, then you want the p, so the probability of success is equal to zero point 0.5, and the alternative is that p is different than zero point 0.5. So if when you have just 1 point value, it's easier to say, oh,
Mhm.
how would it behave under the null? But under the alternative, this is a mess because you have infinite possible values, right? So it's hard to then take the alternative and put the null,
Mhm.
unless you have some cases in which you have only two options, right? For example, it's
Mhm.
either zero point 0.5 or zero point 0.3, then you can do it.
Okay,
But
but
usually
yeah,
you have an infinite number of possibilities for the alternative, so you can't really take that and convert it into a null.
yeah, that makes sense. But if we took something like not the absolute values, but if we say that if we have two coins,
Yeah?
yeah, and if our null hypothesis will be that the coins are the same level of fairness,
Mm-hmm.
so they will always show us the same mean as we go with more tosses.
Okay.
And the alternative hypothesis will be that their fairness is different, so meaning that
Mm-hmm.
their average results will be different.
So, mm-hmm.
So that means that if we have enough tosses, we can reject the null hypothesis, But will it automatically validate the hypothesis that they are different, or still
No.
not? Still not.
Reject the null hypothesis would, so in this case, the null hypothesis will have to be that they have the same mean, right? So
Yeah.
that's the probability of success. So we could
Yeah.
reject that
Hmm.
and say they are different, yes, but we could never accept that they have the same probability of success.
Yeah.
So
Yeah,
we
but we
can
could,
only work in rejecting the fact that they have the same probability of success.
but since there are only two values, like either they are equal or not, we can say that they are not equal. Right?
Yes, but what does not equal mean?
That they have different, that they do not have the same mean. Yeah.
Yeah, but if you look at the difference though, that means that actually the difference in mean is zero or is different than zero. So we are back to the case of before, right?
Okay.
A point versus the rest.
Yeah. Yeah. Well, that's you know, I only did like A/B tests in practice, and I did
It's
not
funny
take.
because I never done it in practice.
You probably would have done it better because
No,
I was mostly using like common sense, and
yeah, but it is common sense. I think these
uh,
hypothesis testing and p-values and stuff are um,
but it's also
is hyper complicated. Yeah.
yeah, and I think people like this question, like how would you explain the p-value to a business person or like non-techie person?
Do you know the definition of p-value?
So I, from my level, that's something like the probability to how to say it. Uh, so the probability to see the probability that we observe just a random data, which okay, so we had these two hypotheses, and we did some observations, and we kind of saw that in a lot of cases the null hypothesis does not hold,
Mm-hmm.
and so, but in some cases it did hold, and I'm trying to understand whether p-value is this amount of hypothesis. Mm, okay, so I think the p-value is the probability of us being wrong when we reject the null hypothesis.
Oh, there is also that definition. I
So, so we think that we think that null hypothesis is
yes.
does not stand, and we reject it. But there might be some error, and not the error, but there might be some possibility that we had just random data, which
Yeah, yeah, this is valid. So basically, it would be under the null hypothesis. How likely it is that we see something as the thing we have observed,
Mhm.
or more extreme than what we have observed. So, like,
Mhm.
let's say you have a null hypothesis and it's distributed like this for something, and then what we observe is in the tail. Then
Mhm.
the probability of observing something more extreme than that. So what stays in the tail, either one side or both sides, that's the
Mhm.
p-value. But this would translate exactly in what you said, right? Which is the probability of being wrong, rejecting the null hypothesis.
I think so. Yeah, I'm just not sure if it's kind of understandable for non-techie people.
No,
So,
for nobody isn't this is understandable.
yeah, but basically, it is the types two or
Yeah, I'm bad with type of errors. But
yeah,
basically,
that's
like maybe we can go now, you use it in practice,
yeah, yeah.
considering the definition is.
Hmm. And also, like I mean, there are also this power of
Mhm.
the test. So this one, I'm really a bit confused. So
I'm also.
yeah, I usually don't really. I just go to some tables where
Mhm.
and pick the numbers from there. So
So
as I just understand, when you planning an A/B test, you need to know like how much time to run it, or for how many.
Or how much data you need, right? Because the
Yeah,
function,
yeah. I mean, how much data, and then that will
yeah,
convert like how many
translates it.
days.
Yeah.
Yeah, yeah, and you have to specify like what. First of all, how precise you want to be. That that is probably as a power, or trying to remember what is a power.
It's something that has to do with the type 2 error.
Uh, yeah, that means that p-value is type 1 error, right? Or,
So no, so the power is the probability that the test correctly rejects the null hypothesis
correct,
when
rejects.
when the alternative hypothesis is true.
And the
So
p-value is the kind of reverse probability.
is 1 minus beta. It is commonly denoted by 1 minus beta and represent the chances of a true positive detection conditional on the actual existence of an effect to detect.
Okay.
Uh,
Well, basically, as I remember, just when you plan this experiment, you want to know approximately what you expect. So, what's
It's the probability of correcting rejecting the null hypothesis, I would say. Yes.
correctly rejecting the null. Okay, but that means minus one minus p-value.
If our definition of p-value is correct.
Yeah, yeah, yeah. Yeah, so basically, this number of experiments that we need will depend also on the effect or the size of the effect that we want to find. I think so. So
Mhm.
yeah, so that means that if we want to find the difference of 20% based on the initial value, we will need like to maybe infinitely toss the coin. But if you want like to stop at some smaller amount, then we will need less tosses. And of course, like the higher p-value we want to, or the lower p-value we want to pursue, the more tosses we will need. So, but the more sure we will be in the results.
Yeah.
Yeah. And so usually when you plan an experiment, you kind of have to find some meaningful values, not to run it for a year, but to do it a bit quicker. Yeah, this common sense explanation.
We also had this discussion once at work. Remember that if we have big data and like the sample size is super big, then we, in any case, we will always reject the null hypothesis.
Oh yeah, yeah. That's. I actually didn't really know like how to do it
Yeah.
in practice, because yeah, if you just look, for example, at the amount at the click rate of something for 2 days, like you have a million events per one day, and even if the difference is super tiny, all the statistical tests will give you that this is significant.
Because you have
Although
so
it,
much data, yeah.
yeah, although it just cannot be true, and I didn't know which formula to pick in this case.
Yeah, I was, yeah, I just think in that case, it probably doesn't really make sense to do hypothesis testing because it's gonna pick up the smallest
Mhm.
difference, right?
Yeah, yeah. Well, but anyway, so you want to jump to something next, or
Yes. What do we want to jump to?
I mean, I'm not sure. Maybe we shouldn't like stay for long. So
It's just the
maybe,
last thing, maybe 10 minutes. Last
yeah,
topic.
maybe it's the last thing. So I would probably jump into something Bayesian vs
Oh,
frequentist,
oh,
as I know that you're like a
oh.
Bayesian fan.
You're going there.
Yeah. So, but I'm not sure what to ask myself,
Well,
and
you
yeah.
can start with the p-value that for Bayesians, the p-value makes sense because the p-value is the probability that a null hypothesis is true, which is much more interpretable than the frequentist p-value, which is the thing we said before. So Bayesian p-value is the probability that the null hypothesis is true.
Oh wow! But how did we jump into this
Yeah,
from?
and the difference is that for frequencies, you always expect the parameters to be fixed, right?
Mhm,
So they have an unknown value that you don't know and you want to estimate, right?
mhm,
Well, it's kind of the same for Bayesian, but we assume that the parameters follow a probability distribution, right?
Mm-hmm.
So, and in this, and in the probability distribution, you express what you think about this, right? So let's say you have a friend that you trust, and then you say, okay, what is the probability of success? I would say, well, the probability of success is probably about 0.5. I trust my friend; he would never cheat. But then you have your enemy, right? And he's the one flipping the coin and gives you a different coin. You would say, ah, yeah, I don't really trust him. I believe the probability that this coin is biased is high.
Mm-hmm.
You can put this information in the distribution of the parameters, right?
Okay. Mm-hmm.
And so if
So
you start thinking in terms of the parameters have a probability, then all the interpretations can be done like, oh, the confidence interval, for example, is the probability that my true value is between A and B,
mm-hmm.
right? Is like, let's say we want a credible interval, Bayesian call it, of 95%. We say, okay, with 95%, my true value is between A and B. Well,
Yeah.
frequentist is like, okay, I have just one experiment, but if I were to repeat it infinite times, of these infinite times, 95%, I would be between A and B. But in this specific experiment, I have no idea if I am between A and B or I'm not. I
So
just
it's
know some theoretical result if I were to repeat the experiment a lot of times, but not about this specific experiment.
not really too practical.
I mean, the theoretical definition is this, right? It's like, okay, I have just one experiment, I have this value. I can calculate the confidence interval that is telling me if I were
Mm-hmm.
to repeat this experiment so many times, 95% my true value would be here. But what about this specific
Mm-hmm.
experiment? I have no idea. It could be in the confidence interval or not.
Okay. Yeah, well, that brings the difference because I never got the practical difference. So this is the
This is the
practical.
I mean, this practical is very different and is interesting because you can use some distributions on the parameter that would give you the same estimate that with the frequentist case,
Mm-hmm.
but with the interpretation I just said. So
Okay.
that's technically why you could kind of interpret the frequentist estimates the Bayesian way, because it would just be the Bayesian way with a specific prior distribution. And prior
Mm-hmm.
distribution is basically the way you express what you think about
Mm-hmm.
the range where your parameter will be.
Yeah. So I mean, this idea makes a lot of sense to me from my common sense level of knowing statistics. That you have some prior knowledge, and then you do experiments, and then you update your prior knowledge.
Plus, I think everyone thinks about statistics the Bayesian way, because if you ask someone that never took a frequentist statistic class, what's confidence interval, it would say the interval that contains the parameter with the probability of, which is wrong according to the frequentist statistics interpretation, but not wrong according to the Bayesian interpretation.
The interval containing the value,
Yeah, the
um,
true value with the probability of. Yeah.
the true value. Okay. Yeah, but in the real world, it wait. That's the definition of Bayesian, or
Yeah, the confidence interval for Bayesians. Yeah.
Mhm. Mm. Okay. Yeah. So I mean, what you see is what you get, more or less. So.
Yeah, kind
Mhm.
of. Because you were brave enough to give some
Mhm.
opinion. And another thing I believe, I don't know, can we go into beliefs?
Of course.
If
Of
we
course.
say something is distributed with this probability distribution, right? We are in any case putting our belief in it. Like if I
Yeah.
say, okay, I'm gonna model this quantity with a normal, or I'm gonna model this quantity with a t, or I'm gonna model this quantity with something else,
Mhm.
I'm already putting a belief in it. So why don't just do it all the way? Because also models are subjective, right? Like
Yeah.
I'm deciding that I want to model the errors with the normal distributions. Nobody tells me that the errors are actually normal distributed. In fact, in
Mhm.
many cases, they're not. I'm reading a book that says that the bell curve is the I don't know, is the biggest mistake ever.
But actually, so as I was thinking about these confidence intervals, I was thinking like that. So you provide like I don't know, 95%
Mhm.
confidence intervals. I thought that means that our value will be in 95% of the cases in this interval.
If you were to repeat the same experiment many times.
Yeah, but this is a frequentist approach, not Bayesian.
Yeah,
Or
because
but for Bayesian, it will mean
in this, so let's say for frequencies it would be, okay, calculate the confidence interval with this specific experiment. And I'm telling you, if you have the condition to repeat this experiment many times, then 95% of the sorry, of the times, this confidence interval would be correct, right? And then Bayesian would say, in this specific case, the probability that my parameter is between A and B is this. So in this
okay.
specific experiment that I've just done.
So there is no real contradiction, I would say. No, is there?
No, I don't think so either. The only thing is that if you are like hardcore frequentist, you would say for this specific experiment, I have no idea if the true value is in this interval or not. It's hit or miss.
Okay, yeah. Then, but since I like data science, applied data science, then
Yeah, in
I would,
practice.
yeah, then I would never do that. So Bayesian.
Another thing why I think Bayesian is cool is that there are cases in which you cannot estimate things with the frequentist approach, right? So let's say you have a problem in which you could, clearly, if you do shrinkage, right? So let's say you have a problem in which you have the same number of parameters as the number of observations, right? Then with the typical frequentist method, you couldn't solve it, right? There would be no solution. So imagine a linear regression in which you have 10 observations and 10 parameters.
Yeah.
Like your whatever, X transpose X wouldn't be full rank, and you wouldn't be able to, or even the opposite, right? In a case in which you have a little observation but a lot of parameters, or so on.
Like deep learning. Yeah, but I get it.
Deep learning, you have a lot of data though, and a lot of parameters.
Yeah.
I mean, you need a lot of data for deep learning, right?
Yeah, but it also, yeah. I mean, with some regularization stuff, you can have
But a
sometimes
typical
more
example
parameters.
is like genetic studies, let's say, because let's say you have a regression, right? And you want to predict if a person will get an illness or not, right? So basically you have, let's say, 10 people, but for these people, you have a lot of predictors, right? So a lot of X's. So you have, I don't know, all the blood tests, right? And then you put it in a regression model and you have your Y's are, will they get, like this person got sick or not? And your X's are all the blood test level of different things. And so for each blood test indicator, you have one parameter, right? And let's say you have 100 of these in a regression model, right? So you have 100 X, so basically 100 parameters, 100 beta, but only 10 Y's. And with a typical frequentist method, there's no way. This is just not
Yeah.
is a linear algebra thing. You have a matrix that is not full rank, you cannot solve it. And so the way frequentists deal with it is with shrinkage. Well, either you do variable selection from the beginning a lot, or you do like, a few variables at a time, or you do shrinkage usually, lasso
Rich.
ridge regression, right? This kind of stuff. But all of these are putting information in, right? Because for ridge regression, basically you're adding a penalization term, right? Which is also subjective, and also for lasso. And this, if you then, okay, maybe I'm going to technical, but if you then look at the likelihood, right? So then you look at the distribution of the y, and you have this plus, and then you have the penalization term. Then you take this, you take it out of the exponential, for example, in case of normal regression, and this becomes your Bayesian prior. So it's, this like shrinkage, like ridge regression and lasso regression are exactly equivalent to Bayesian methods.
Nice.
Exactly, like down to the, yeah.
Yeah. I mean, yeah.
So why should you yeah, so this is one of the,
That's actually cool. Yeah, and that brought up one another topic. Maybe it could be the last one for us.
okay.
So this sometimes people ask you like, how can this or that problem or task be solved, and they usually mean that there is maximum likelihood approach, and also how it's called a map, so a posteriori,
Maximum a posteriori, yeah.
maximum posteriori, yeah. So, and I'm always confused when it goes to these technical definitions. So this maximum likelihood, as I understand, you kind of have your real data, and then you have some theory, and then you want to see how this theory matches with the real data that they observed. So, like,
Yeah.
how
How likely it
likely,
is, yeah.
yeah, how likely is it to receive this data given that your theoretical assumptions, and then you calculate this difference, and then you find the extremum of this difference and find the
Yes.
parameters from this.
Yes.
So this is more like differential equations. I
Yeah.
mean,
I mean, yeah, very simple ones.
yeah. I mean, very simple ones. Yeah. So you just have your function and you find
Uh,
the maximum or the minimum. So this is the maximum likelihood approach, right?
yeah, but in practice, so in practice, like, so there are some problems for which you don't need a distribution, right? Because, for example, if you want to do a linear regression, you don't need a distributional assumption, right? You just need to say, okay, the errors have a mean 0, and you can get your how is it called, that estimator for linear regression?
Estimator?
Yeah, I
You
don't know,
mean
the sum of squared minimizing the sum of squared
means
residual. It has a name, but I don't remember. So you get that estimator, right? But you didn't really assume any distribution. But if you want to do testing, for example, or p-values, you will need to have a distribution on the errors. But then there are other cases in which you cannot do anything without assuming already a distribution. So let's say you're talking about a positive, like you're talking about, I don't know, queuing times or like time to answer the phone. A lot of times people would already put a distribution on it. And in the case in which you have a distribution, the only way to estimate something, I mean, the most common way to estimate something is to take into account this distribution. While for simple linear regression or linear regression, you don't need any distribution unless you want to do testing or inference or confidence interval. For other problems, you have to, right? So if you have Poisson regression, you're just assuming a Poisson distribution. And once you
okay.
have a distribution, then you are going to use maximum likelihood. I mean, this is how I see it, because it's the only way that you can go and find an estimator. Yeah. And it's exactly as you said, is basically the maximum likelihood estimator for the parameters is the value of these parameters that are most likely to give me the data that I observed under this distribution, though. So again, we are assuming a distribution.
And this trick of maximizing or minimizing this cost function, or how we call it,
Yeah,
it's just a
exactly.
mathematical trick.
It's just optimization. It's like, I don't know, we did in high school, right? So you take the first derivative, you put it equal to 0, and then you want to know if it is a maximum. So you take the second derivative and make sure at the, like, around the first derivative, this is greater than 0. And then, of course, you might have problems where you have local maximum. So for easy distribution, this is never, like, is never a problem. But if you have complex distributions, then you need to be careful about that too.
Okay, yeah, that makes sense. And what will be the map, maximum posteriori?
Is the same, but for a posterior distribution. So it's in the Bayesian sense. Is you take the prior, the posterior, the likelihood, you combine them, you get a posterior distribution, and then you take the maximum of that.
So basically the same, but just different distribution.
Same for Bayesian.
Okay.
Then there is something else, right? No, I don't remember if there is something else. No.
Maybe. So next, yeah, I will just.
Because for Bayesian, you can have, so since the posterior distribution is, so for in the Bayesian case, for example, you can take the maximum posterior or also the posterior mean, because the posterior distribution is not symmetrical usually. So, I mean, the mean and the maximum will coincide only when you have a symmetrical distribution, right? And if the distribution is not symmetrical, then yeah.
Yeah.
You can pick between the two.
Yeah, I cannot quickly Google anything else.
Yeah,
Mostly
but
it's
it was
this.
good. Thanks for asking. I miss a bit
Yeah,
doing stuff, but I don't know what practical utility it has in a real world.
you never know. It's
You know, I just keep it into my mind.
yeah. I mean, it's kind of fun. So you
I mean,
know,
I know this stuff gets asked a lot of in interviews, and I think it's like also a lot of the reasons why a lot of people with like, I don't know, PhDs or a lot of academic knowledge, especially in Silicon Valley or so, get hired by big companies because they really focus on this kind of knowledge. But I don't know how much this kind of knowledge will make you a good data scientist, because I've never
I
used it in real life.
yeah. I mean, it depends. If you're a data scientist who is mentoring other data scientists, then it could be meaningful. If you're
Or
just
maybe for a research scientist or some, yeah.
yeah, you know, like our life is so diverse, and sometimes you need this, sometimes you need that, and it just yeah, nice to know that I can go to you and ask about statistics. Let's see like
So I
this.
remember more than I thought, basically. That's what
Uh,
we're saying. But yeah, of course.
I mean, I'm saying that you're smart, so
I'll come to you
it's
for MLOps. I'll come to you
well,
for APIs. Can we do that next time?
yeah, that's actually a nice topic. So hey, we announced it. So in some time we will have the similar session about how you can deploy something like with yeah. I mean, you mean like how we can deploy a model?
Yes, or
Or
like, yeah, or like a Flask API or a Fast API.
yeah, Fast API. Yeah, I actually still have never touched Fast API, and
Just do
it's
Fast API.
yeah now it's
Real
trending
life.
as I see.
It's
Yeah,
trending, yeah.
cool. Yeah, so definitely let's do it. But I suppose it will need a bit of preparation for this, or you can go with the flow. With
No, I don't think I can.
yeah. Well, but anyways, also yeah, let me show it. I'm very proud of this comment, and thank you, Alex.
Thank
This
you, Alex.
yeah,
Oh,
we
that's
are
nice that you can show it.
yeah. So well, I think we really rocked this morning. So yeah, thank you very much, Annalisa, for coming
Thank
and
you, Igor, for inviting me.
yeah, guiding me. Yeah. So hopefully we'll have
In the
more and
meanwhile,
more
I took
sessions.
notes and my hands are completely blue with the wrong pen.
Ah, yeah, you were writing a lot. Yeah, and yeah, Alex says that. So he was.
If you need to read a statistics book, wait, I have it. This is the best book ever. And it's a book that also, this is the last thing I'm saying.
Yeah,
I mean, I love it.
Alex.
It's
Yeah,
not, yeah, this one.
but
The
fast
elements of
Ferrari.
statistics. Yeah. I
Oh
love it.
my. Yeah, but that's
It's the
something
best book ever.
I would have the same comment as I think I tried to start this book at least 5 times.
It was this book, Alex. This is the best book ever because for statistician, it makes you understand how machine learning works, and for machine learning people, how statistics works.
Yeah, it's supposed to, at least. Didn't really work for me, but no, I mean everyone says that it's the best
I
book.
mean, can
So
I use this session for a bit of self branding?
yeah, yeah, right. Of course, you have your own book. Of
Also,
course,
this
show
book.
show it. Annalisa wrote a book. Yes.
I mean, I didn't write a book.
So
I
the
wrote
handbook of
something. There is my last name there.
you wrote a significant part of it. So yeah, you
No, I just
see,
put
it's a
much
handbook of data science in the yeah.
but it's not
And then
as
you
good
can
as.
maybe show it closer. There's your name. Come on, show it closer.
Here. Oh wait, there is my.
Maybe a
Wait.
bit. Yeah, you see Cadonna. So
Among
Cadonna,
so
that's
many people, there's
Alisa.
also me.
Yeah, Annalisa Cadonna. So she wrote a book. Awesome. Yeah.
Okay.
Well, yeah.
Thanks, Igor.
Thanks a lot, and thanks everyone for watching this. And we see you next time. Thanks, Annalisa.
Bye
Have a
bye.
nice evening. Oh, evening.